Uh, Welcome back after a long break. I think there was 1 week break, but then this is almost after 2 weeks that we are meeting. And I hope you went through the previous lecture at least once, because this is going to be continuation of whatever you were discussing. But before we begin, few things to announce. So first of all, I made all the announcements required for the project. Now, well, I already apologized, but I will still do it again. So sorry for the delay. One of the reasons for the delay is the fact that we haven't covered advanced stuff yet, and students were finding it difficult to find papers which they could do as a project. Okay, so as I mentioned in the beginning of the course, my plan for the next year is actually to remove the project and have a fourth assignment, since this is an introductory course, and I will be teaching an advanced second course in winter, which could have a project component. Okay, so this is something that I learned from this course. I'm sorry for keeping this project this semester, but that is why TAs spent a lot of time to come up with these papers, which I have listed in the Google Doc, which doesn't require a lot of deep reinforcement learning. Okay, so we will not see a lot of deep reinforcement learning in this course. We focus on the classical oral, and almost all the papers that has been listed as examples for the projects. So they have simple tabular experiments and linear function approximations. At max, small neural network experiments. After today's lecture, you should be able to do that as well. Okay, so that is one good place for you to get started. And I know a lot of you are coming to my office hours to talk to me about your project ideas. Continue doing this. So the deadline for the initial proposal is only next week. So you still have 1 more week to decide what you're going to do. There is another thing that I want to highlight, which is for both projects and the assignments. Okay, so in general, I get the feeling that students think the assignments are long. Okay, I want to remind you a few things. So first of all, I see that a lot of other courses have a midterm and end term. We don't have a midterm. Okay, my general philosophy is this is a grad course. You're not here for exams. You're here for learning. Okay, so and you learn, and almost every feedback that says assignments are for every feedback that I get that assignments are too long, there are also feedbacks in the anonymous form which says assignment is long, difficult, but I learned a lot. Okay, so there are a couple of things that I want you to optimize. One, there is no midterm, so whatever preparation that you're going to do for the midterm in other courses, it's kind of substituted with some extra time for assignment. Two, we don't have the mandatory 3-hour labs, right? So I also included that in your assignment time. If you have questions during the assignment, you have an office hour, you go for that day's office hour, your answer is you get your doubts resolved, right? So it's kind of asynchronous, which gives you some extra time to do the assignment. So these are two reasons why the assignments in this course could be slightly longer than the other courses. Okay, so take that into account when you're preparing for your assignments and the project. Okay, so in terms of project, remember that this is a team of pre-project, which means it should be 3 times the work. So you cannot do what one person can do and the others not doing anything. So in the past, whenever I had projects component, I would always have 2 teams coming to me and say, hey, my teammate did nothing and you should not penalize us for that. Okay, please don't come to me with that request. It is your responsibility. So your team is your responsibility. So you find teammates with whom you can work properly. All 3 of you should contribute, and well, not in the sequential order, in parallel way, so that you can finish this in a month. Okay, so any questions about the project? A lot of you were already clear on what you want to do by discussing with me for the last 3-4 weeks. I think those students have already submitted the proposals in the grade scope. But for others, so there are papers available to pick from the Google Doc. You can pick one of them and write your proposal and submit it next week. Is that clear? Any questions in the chat. There is a chat question. Okay, so there is a question about what if two teams choose the same paper? Okay. Now, there are 15 papers listed. Like, if we run out of that, probably we will add a few more. If you're picking the same paper as someone else, given that there are 10 more papers like not picked, then probably consider picking those papers which are not picked. So whenever you pick a paper, like just add a comment there so that people knows that you're using the paper. Okay, so try to distribute. Like it is not too bad if two teams work on the same paper, but I don't want 5 teams to work on the same paper because it is a grid world experiment. Okay, so maybe 2, but definitely not more than 2 teams. And even for the 2 teams, like you should justify that there are no other papers which are currently. I think there are not more than only 4 or 5 papers have been picked. There are still 10 more papers. So probably I'll ask TAs to add 5 or 10 more today. Okay, so we will add more papers. Like so, try to spread out. There is also another question. So what if I'm not finding a third teammate? So well, like you. Oh, there is a question about can we propose our own paper? Yes. If you're proposing a project with your own paper, that is all welcome. Okay, so this list is for people who cannot find a suitable project. So it's good if you have a project already. And what if I'm not finding a third teammate? So well, use Piazza, talk to people, try to find a third teammate, and come to class if you want to talk to people. So well, like maybe there are valid reasons you are doing this class remotely, but for others who are just watching the recording and not coming to class, not coming to Zoom, come to class like so that you can talk to others and find a teammate. We really don't want less than 3 in a project for the first 3 tracks. Okay, so less than 3 is allowed only for the research track. Like we don't want to evaluate 100 projects. Evaluating projects take a lot of time. Like so, like it's much more deeper than assignments. We don't want to increase the workload for the TAs. Okay, so please try to form a team of 3. Okay, so I think we can get started. Yeah.
Can you please make an announcement on final exam dates? Because we have other courses taking exams, so we don't want to overlap.
Okay. First of all, okay, I think this is because you are not from Poly, right? So
yeah.
Poly students, do you already know the exam date? Is it announced? So exam dates are not in my hand. So exam dates are decided by the university, like for the courses, and they put out the schedule probably in few weeks, I guess. Like so, I'm not sure when. Like probably November. Like so, the university is going to put out the schedule for exam. So maybe once I will check if it is already out. If not, I'll find and send an announcement like whenever I have the date. I cannot change the dates. Okay, so like usually there should not be any clash, but people from other universities might have clash. If you have clash, come talk to me, but usually there should not be. The chances of 2 exams clashing is rare. So, and also our exam is not physical, like it's take home, so you can do it even remotely, but you will be doing it remotely. And okay, so someone in chat says it is not yet out. So well, I think I encourage the Poly students to just post the exam date in Piazza whenever you find it. It's for students who are from UDM, McGill, Concordia, and other places. Okay, so we have a lot of students who are outside Poly in the course. Okay, so I think that's a lot of time for announcement. Like we should begin. So in the last, well, I'll give a very quick recap of last week before we start. So I think we started with value function approximation last week, right? Now, a quick recap even before that, right? Like so, we discussed many solutions for solving reinforcement learning. First of all, we pose reinforcement learning as a Markov decision process, right? Like so once you have the MDP, then if you have access to the model of the world, like the dynamics function, then you can use methods like dynamic programming, right? But if you don't have access to the model of the world, then you have to learn the value functions instead of trying to estimate it from the dynamics function, right? Like, so now, what are the two major learning methods that we have seen in this course? Quiz. TD, okay, so temporal difference learning. So what else? Monte Carlo, right? So Monte Carlo is a sample-based approach, which basically waits for the entire episode to finish, and then you estimate the returns, like sample returns, and you average the sample returns. On the other hand, like TD is bootstrapping method, like dynamic programming, in the sense you update as soon as you see the next state, right? Like, so it's like one-step update, and we discussed advantages and disadvantages of both the methods, right? Like, so for example, when you have a continuing task, or when you have a task which has very long time horizon, then Monte Carlos could be, well, first of all, in continuing task, Monte Carlo is not possible. Like, and in long horizons, Monte Carlo could be extremely slow. While TD doesn't wait for the episodes to terminate, it just learns one step after another, right? So, and we can also combine the advantages of both. How? Yeah, by doing n-step TD, right? Like, so instead of taking one-step TD, I can use the actual return until n steps, and then truncate the return there, and use my approximation there, right? Like, so you can kind of combine both by n-step TD, right? So that is what we were discussing for the first few lectures, right? Like, so then last lecture, like, we started thinking about other problems that one would face in, like, while solving reinforcement learning. Like, so specifically, like, we started with this one specific problem, which is like, what if I have like really large number of states, right? Like, so most of the real life problems that we would face is going to have lots and lots of states. Now, in such situations, doing a tabular approach where you explicitly maintain a table of value functions, right? Like, so, like, you have a list of S1 to Sn, okay? And like, for example, in the case of, let's say you want to do TD prediction, okay? So then you want to estimate the state values. So you will be estimating the V function for all these states, right? Similarly, like, if you want to do control, then you want action values, right? Now, for every state, for every possible action, like, you have this table, like state 1 to state n. So Q value of action 1, Q value of action 2, and so on, right? So far, like, until last week or last lecture, like, so we were looking at what we would call as tabular methods, which is what you're even implementing in your assignments, which is the idea of explicitly listing all the states and then updating all the states until convergence, right? So now this is simple and almost always converges to optimal solution or near optimal solution. It's all fine, right? Like, so, but then the problem is, what if I have like millions or billions of states that I cannot even go through them like once or sufficient number of times, right? Like, so now the classical example that I always give is backgammon, right? Like, in the case of backgammon, there are 10 power 20 states. Now, even going through all the 10 power 20 states once is not possible. Like, so it's going to require you thousands of years to like solve backgammon by using, let's say, dynamic programming. Okay, now what do we do in those situations? So this is where the idea of value function approximation comes into picture. So the idea of value function approximation is, for every state, let's take ST, okay, I'm going to represent the state. Instead of an entry in the table, I'm going to construct some features for the state. And I'm going to represent the state as X of ST. Okay, so to give you some example, let's say let's take self-driving cars, okay? Now, there are infinitely many possible observations or state observations possible for like the self-driving car, right? Like, so now you can construct a feature space by considering things like what is the speed of the car, like is one feature. Are there any pedestrians walking as another feature? Like, so like what is the velocity? Like, so what is the angle in which you are moving things, right? Like, so like you can, like, is there a truck behind you? Like, so you can construct hundreds of features like this. Now you'll feed this feature vector as input to the agent. Now the agent is going to make decisions by looking at these features. Is it clear? Now, I'm not going to get into the details of all the on-policy value function approximation that we discussed last class, right? Like, so, but specifically in the last lecture, we focused on on-policy methods, okay? Right? Like, so, like we looked at on-policy methods and we basically changed the algorithms, like from using a tabular approach to a parameterized function approximator approach. And almost all the cases, it was very trivial to change. Like all you really need to do is to change your one line, which was previously doing updates to the table, to updates to the parameter by using gradient descent, right? And we also discussed about like how to construct these features. Like, so for example, can someone tell me example feature construction methods that we have seen? People in chat or in class? So well, there are some answers in chat. So we saw course coding, tile coding. What else? So what are the various feature construction methods that we have seen? You don't have access to the notes of the last week.
State aggregation.
Sorry?
State aggregation. State aggregation.
Yeah, you can do state aggregation, right? Like, so the idea of state aggregation is like if you have 1,000 states, you just aggregate it into 10 states, 10 groups of like hundreds, for example, and then like you consider that to be doing, like you consider doing super updates instead of just simple update per state. Yeah, okay. So what else? We saw coarse coding and tile coding, where the idea is you take the spatial structure, like you construct coarse circles or tiles, and like they have, and you have overlapping tiles, like which would help in generalization to unseen states. What else? Sorry? Yeah, polynomial functions, right? Like, so you, like we talked about basis functions, like, so you can have polynomial basis functions, like where, like you take a bunch of features, now you want to like consider all the interactions between the features. So you can do x1, x2, x1, x3, x1 square, x2 square, and so on, right? Like, so we discussed various like ways in which you can construct these features. But once you construct these features, then the value function approximator was given by a simple linear function, right? So you have a bunch of features x, right? We have like our value function, like v, this is the estimate. So I'm going to call v dash of yes given w, right? Is nothing but w transpose x, right? So we had a very simple linear model which took all the features and tried to approximate the value. Now the advantage of having such a system is now you make updates to w based on one state, you are affecting the value of all the states, right? So you can generalize faster, like, well, first of all, in tabular methods, you cannot generalize from one state to another state, right? Like, so for example, like let's say there is some value for the state. Well, if you're bootstrapping, there is some generalization happening. But most, if let's say Monte Carlo, right? So in Monte Carlo, there is no generalization across states, yeah?
And I just want to understand something. In the tabular methods, when you have the states, even though like state can be represented by features,
There's no use in doing
X,
that.
Y position, the state like the algorithm doesn't care about the features.
Yes.
Okay.
Yes, in tabular methods, like algorithm doesn't care about the features because it's just tabular. Like so you are updating values, like you have a vector, value function vector or a value function table. But the features become more useful once you start doing function approximator. Okay, so now the advantage of this is like now I can see a completely new state which I have never seen before. But my value function estimator, like the value function approximator, can give me an approximate value for this state, even though I have not seen this state. And this is not possible with tabular methods. Okay. Okay. I think this is a long summary of what we did before. It is what it's because some of you might have forgotten like what we did before. Now, so in today's lecture, well, like there are couple of things we are going to do. Like first, we are going to move from linear function approximator to nonlinear function approximator. And we are also going to discuss about how to do function approximation with off-policy learning, which is very challenging when compared to like simple on-policy function approximator that we have seen so far. Okay, so first let's talk about nonlinear function approximators. Okay, so first of all, the linear function approximators that we have seen, right? Like so we had of let's say double transpose, yes, right? So this is very limited in the sense it's just linear, right? Like so, like you cannot do like much in terms of the interactions between the features. If you have to consider complex interactions between the feature, okay, there are two issues here. Okay, so first of all, this is a really simple model that it requires carefully handcrafted features. Okay, so depending on how you construct your features, you can make the problem hard or easy. Okay, if you give all the information required to make the decision, then probably a linear function approximator is suffice. Like so, it is going to consider everything and tell, okay, this is the action that you should take. Is it clear? Let me give you an example. Okay, so let's say you are in a game where there is, well, I'm very bad in drawings, but let's say this is the enemy, okay, and this is you. Let's say you are in the simple game, like where your goal is to just move away from the enemy as much as possible. Okay. Now, if I construct my features carefully such that I encode the distance from the enemy as one feature and the speed at which he's moving as another feature, right? Now, it might be easy for simple models to just take this information, and this is an easy control task in the sense you should always just move away, right? Now, if I give you this information, then you can easily do this. Instead, what if I just give you the visual observation? I give you this image which tells you where you are and where the other person is. Now this becomes a difficult task, right? So it becomes difficult because now you have to estimate how far is this person and like how is this person moving, and you need to recognize this person, right? So there is additional perception challenges, and like there are a lot of other additional challenges involved in getting information from the state. Then you make the decision, right? Like so now it is very, very crucial how you construct your features, right? So this is a bit of a problem because now you need to spend a lot of time in handcrafting these features for every task. Like for example, let's say you are a company just focusing on one application, then probably it's a good idea to spend a lot of time on handcrafted features for that particular task. Okay. However, like if you want to try different applications like over time, like let's say you are a service-based company, like who proposes solutions for different other people's needs, right? Like so now you don't want to handcraft features for every project, right? Like so you want something which could handle all sorts of input representations or input features. Now, This is one of the problems with linear function approximator. Okay, it requires carefully handcrafted features. And the second problem is the interactions between the features is limited. Okay, because it is a linear model. In fact, in a linear model, there is no interaction between the features, right? Like, so you have W1x1 plus W2x2 plus W3x3. So maybe some simple additions, but nothing more than that, right? Now, the question that we should ask here is like, so can we do better than this, right? Like, so now can we come up with a method which would, let's say, automatically learn the features and the interactions between the features, okay? If we can automate that, then we have added an extra power to all the RL algorithms that we have seen so far, because now I can apply these algorithms for any task and with reasonable extra work, like, so it is going to perform out of the box, yeah?
Is the first reason because there is no interaction?
Yes, yes, yes. Well, they are related, yeah. Okay, now, so this idea of learning better state representation, right? Like, so like learning a better representation for my state so that I can estimate the value functions efficiently, right? Like, so this is known as representation learning. Okay, so here is the general idea. So the general idea is like, I want to start with some raw features, which are what the environment is giving me. Okay, so now it could be easy if the features are nice, but sometimes I might get like really raw features, which is just, for example, in the case of a robot, like imagine a robot walking around this room and its camera observation is what it gets. Now this is like this is probably a low quality image, and it's a complex image because like now the robot has to reason about objects in the image. Like it has to detect objects, it has to locate the objects, and it has to consider the interactions between the objects and so on, right? Like if it is a video, it has to consider the temporal interactions as well, right? Like, so imagine a robot which is trying to cross this like path, and if people are moving around, it has to consider that temporal aspect as well. Now, the idea is like we feed all these raw features that we have, okay, and we are going to have a representation learner, okay, which is going to learn this X of S. So previously, I was constructing this X of S, like I was constructing it by giving features, by using polynomials, by using tile coding and like coarse coding and so on, right? Like, so instead, can we have this learner like which is going to take the raw feature and give me X of S? Then I pass this X of S to the usual linear function approximator, okay? And this linear function approximator is going to give me the value function. Fine. So this is what we are going to do, and specifically this representation learner is going to be a non-linear model. Okay. Why? Because if you have a linear model for X of S followed by linear function approximator, then it is essentially equivalent to just having one linear function approximator, right? So there is no use in having a representation learner. Well, maybe there are some practical advantage, but usually there's no use in having a representation learner if it is not linear, if it is not non-linear. Okay, so you have a non-linear representation learner followed by linear function approximator. Now, this is not a machine learning course, so I'm not going to teach what is neural networks here. Okay, so I will give you a very abstract, high-level introduction to neural networks. Okay, now neural networks are probably the most successful class of representation learners. Okay, now I'll give you a very high-level abstract introduction, which is sufficient for us to continue with the rest of the course. But if you are interested more about learning neural networks, like so, you should do a machine learning course or a deep learning course. I know a lot of you are in my machine learning course. Like, so you'll be seeing neural networks in a few weeks in ML. But if you want to learn more about neural networks, like there's a deep learning course at UDM in the winter by Aaron Corbin. Okay, now what are neural networks, right? So neural networks are function approximators, which take some input and construct some latent representations. Okay, now these representations, latent representations, are learned from experience. And imagine like you have a network which takes the image and tries to construct representations which are what are the objects in the image, like, and how far is one object from another, where is the enemy, like, so where is your location. Okay, so imagine a network which decides, like, which figures out all this by itself, right? Like, so now roughly, like, neural network is going to have a bunch of layers. Like, first we start with your input features. Okay, now from the input features, we are going to construct some hidden features. Okay, now the way in which it works is like it is just a fully connected network. Now imagine your input is x, right? So you have an input x, which is a bunch of features. Okay, so we're going to call this as, these are raw features, and we're going to call this as input layer. Okay, now from this input layer, there are some connections. This connection is a matrix W. Okay, and you have some hidden features that you are learning, or let's just call this as learned features. Okay, once you have some learned features, then you can pass this to the linear function approximator. Okay, so my linear function approximator, let's say there are, well, maybe we are doing value function approximation. Sorry, we are doing value function approximator, right? So there's going to be only one value that we are estimating for the state. Okay, so now this is my output layer. Fine. Let's just call this as W2. Okay, let's just call the hidden layer as H, and let's call the output as O. Okay, now maybe it is easier to understand this like once I convert this into equations. Okay, now given some input x, my input is the state representation x. Okay, first I compute my learned feature or the hidden representation. Let's just call it H. Okay, which is basically some nonlinear function of W1x plus B1. Okay, so given x, I do one linear layer, like so W1x plus B1 bias. Okay, and then I add some nonlinearity f. Okay, now this is a new representation. H is the new representation for the stage, right? So once I have this new representation, which is learned, I can actually pass this to my value function approximator. So my V of S, given the entire neural network, is basically let's just say W2H plus B2. Is that clear? Now, if you think about it, this part of my network, right? Like, so this is the representation learner. So once I have the representation, then I feed it to my linear function approximator. So this part is the linear function approximator. Is that clear? So now, if you think about it, in the case of polynomial feature representation, right? So we did not have this part. We constructed our polynomial features. You can imagine H to be the polynomial features like x1, x2, x1 square, x2 square, x1, x2, right? You manually constructed H for polynomial feature representation, and then you fed that to the value function approximator, right? Similarly, even for tile coding, you decided all the tiles manually, and then you constructed H to be this one vector which has 1 or 0 for all the tiles, and then you passed that H to the value function approximator, right? Instead of that, we are taking a general approach here. Like, so we have our feature construction here, but this construction now has parameters W1 and B1. Now this W1 and B1 is going to it's going to decide like how my features are going to be constructed. Now I can actually learn this W1 and B1 by just doing gradient descent with my value function loss, right? Is that clear? Any questions? Any questions in the chat? There's a question. So can you force neural networks to choose the simplest representation? Okay, that's an interesting question. So now this neural network is learning a representation, right? Now the question is, can you force this network to choose simplest representation compared to complex representation that achieves same accuracy? Yes, it is possible. Like, so for example, you can force this network to be sparse, like more close to linear. You can regularize this network to like whatever way, like to make the representation simpler. But probably we will not talk about that in this course. Any questions? Well, this is probably the simplest 5-minute introduction to neural networks. Yeah.
You wrote H equals F of something. Is it H equals the something? Like my question is, what is F?
Oh, okay, that's a good question. So what is F, right? Like, so F is some nonlinear function. As I mentioned before, you need some nonlinearity. Otherwise, okay, so let me go back.
Where would be F on the graphical representation?
Yeah, I'll come to that. So first of all, let's just say H is equal to sigma. Okay, let's say there's no nonlinearity. Okay, so let's just say I have something like this. Value of state given the neural network is equal. I'm just going to consider all the parameters of the neural network to be theta. Okay, it's going to be, let's say, W2x plus B, so W2H plus B2, right? So theta is basically all the parameters of this model. What are all the parameters here? So what are all the parameters here? Yeah. W1, B1, W2, B2, right? Okay. So given all these parameters, like let us say there is no nonlinearity in my H. Now, this is just one linear equation followed by another linear equation, right? Like, so you can represent the same thing as another linear equation. So there's no use in like doing this, like if you don't have nonlinearity. So we are going to add a nonlinearity, okay? Now, this nonlinearity, like we're going to call this as some nonlinear activation function. Okay, there are many nonlinearities that people use in the literature. Like, so for example, you could use sigmoid function, okay, which is sigma of A is equal to 1 by 1 plus e power minus A. Or you could use tan H function. So tan H of A is given by e power A minus e power minus A by e power A plus e power minus A, okay. Or you can use ReLU, which is rectified linear unit, okay, which is basically max of the A, max of 0 comma A. Okay, so roughly sigmoid will look something like this. Tan, which will also look something like this, but with different range. ReLU is going to look something like this, like where it is 0 for all the negative numbers and like and linear for the rest. Is that clear? Okay, now there is no need for stopping here, okay. Now I can actually make this network even more powerful by adding more nonlinearity. So the more nonlinearities you add, you have more nonlinear interactions that you're capturing, right? Like, so for example, imagine I'll come back to your question. I did not forget it. So for example, imagine like you start with X, okay, and you construct first set of learned features, okay, Now treat this as input to another connection. So you consider the second set of learned features, okay, and then you pass it to the value function approximator. Now you have two levels of nonlinear interactions. That is going to give you very complex representation that you can normally not get with just one level or like linear function approximator, right? So there was this question, which is where would the activation function, like f written in the graphics, right? So usually it is here, like so. Once you compute the value here, like you apply the function. Is it clear? Now, this is all good. Now, the question is, okay, maybe let me write the equation for the second thing, right? Like, so, like H1 is given by, let's say we are using sigmoid for nonlinearity. Sigma of W1x plus B1. H2 is given by sigma of W2x plus B2. And then 0, like, sorry, output is given by W3x plus B3. Okay. Now, how do I find these parameters? Okay. The good thing is we have already seen the basic tool, which is the idea of gradient descent, right? So I can compute gradient with respect to these parameters and then go in the opposite direction. So the idea here is like we are going to find those W1, B1, W2, B2, W3, B3 that gives me the least possible VE bar, like the value prediction error. Okay. Now, in such a layered architecture like neural networks, right? Like so, computing the gradients for things which are internal, right? Like W1, B1, W2, B2. So this can be done much more efficiently if you use the backpropagation algorithm. Okay. So backpropagation is not a learning algorithm. Okay. Now our learning algorithm is still gradient. Like we will use gradient or semi-gradient, but like if you're doing on policy learning, we will be doing, okay, depending on whatever cases, like we will either do gradient method or semi-gradient method. But backpropagation is just an efficient way of computing the gradients or semi-gradients, like before we apply it. Okay. Now, okay, yeah, there was a question. Yeah.
Yes. For example, for H2, why is it W2 of X?
Oh, sorry, it's a mistake. H1, sorry. H1, H2. I think that even the note has this mistake. So we should. Okay, so now, yeah, so backpropagation is just an efficient way of computing the gradients in the inside the network, like by using the idea of chain rule. Okay, it's really simple. Let's say I want to compute the error with respect to weight W2. Okay, now, so this, my loss is going to be, let's say, O minus whatever value estimate the whole square 1/2. Okay, I'm doing a squared error between the model network's prediction O and the true value function, let's say. Okay, now you see that this loss does not have W2, right? However, we know that O has H2. O is a function of H2. H2 is a function of W2, right? So I can actually compute dou loss by dou W2 by dou loss by dou O, and then dou O by dou H2, and dou H2 by dou W2. Is that clear? Now, this neural network that we have seen here, right, is an example for what people call as fully connected network or a multi-layer perceptron. Okay. Now there are many variations of neural networks are possible. Like for example, instead of having, you can also call this, people also call this a feed-forward network. Okay. So now, if some internal representations have some loops, then you have recurrent neural networks, okay? And there are many other variations possible, but it is not the subject of this course, okay? So for now, when I say neural network, it could be anything. Like, so when you read a paper that says, I'm using neural network as a function approximator, like you should try to understand what is the neural network that they're using as a function approximator. Like, so most often you can implement this simply, and we will be having a tutorial on PyTorch, I think October 27, right? So check the calendar, like check this lab, like schedule page, I think October 27. So we'll have a tutorial on PyTorch, like, so where like you will be explained like how to implement these things like by yourself. So, well, probably I just want to do one more things before we stop for break. So now, when you have images as input, okay, which is often the case, like when you are designing an agent to play games, right? Like you see the current observation, and it is often the case, like when you have self-driving cars or robots with vision, right? Like, so whenever you have the visual images as input, okay, now there are better neural network architectures available for doing function approximation, okay? So these are called convolutional neural networks. Okay, now convolutional neural networks exploit the spatial structure of the image. Okay, so we will not get into the mathematical details of CNN, but I just want to give you a very high level overview. Okay, so CNNs basically have, like, they basically take the input, okay, which could be some RGB images, like so in this case, this is a grayscale image of 28 cross 28 pixel. So it is 28, but imagine you have an RGB image as input, okay? So then you're going to have 28 cross 3 channels, RGB, right? Now, the learned layers in a convolutional neural network, like unlike the MLP, is going to be visual features, okay? Imagine like you look at small patches of images. It's kind of like tile coding, okay? You look at small patches in the images and you construct a feature map based on these patches, okay? Now you construct hundreds of such feature maps. Now, to reduce the number of features, people do something like max pooling, where the idea is you consider 4 different maps, you get the maximum feature out of it, okay? So often CNNs would have this convolutional layer or conv layer followed by max pooling. So then there'll be some nonlinearity. So you have convolutional layer, then some nonlinearity, then max pooling. Now you repeat this like as many times as you want. So another convolutional layer, nonlinearity, max pooling. Another convolutional layer, nonlinearity, max pooling, right? So after how many ever layers you want, then you need to give this information to the linear function approximator, right? Like, so now you have to take all these feature maps, which are matrices, flatten it out, and construct this one flat representation. Then you pass that to the fully connected network. Is that clear? So again, if you want to learn more about convnets, like, so I encourage you to like read online. There are a lot of resources. Like, there is also a very good Stanford course on convnets, CS221, I guess. Like, I'm not sure. But for the purpose of this course, like so this is all we talk about neural networks. Okay, so like moving forward, whenever we have image observations, we are going to use convnets. And whenever you just have simple vector representations, we are going to use neural networks. Is that clear? Any questions before we go for a break? Any questions in the chat? Okay, well, I can also take questions after the break. So let's stop here and resume at 10:32. I'll try to go get coffee.